In this problem, we are given an integer array and we have a target. We just need to find three integers from that array such that the sum is closest to target. All right. I would like to think of summation as just a bunch of numbers. Like let's say I am summing a plus b plus c. So if we sum this triplet, we will get a number. And one observation about this is that we can think of summation as kind of like unary operators bunched up together. Let's say I am summing 3 plus 5 minus 7. Now think of this sum as plus 3 plus 5 and minus 7, and they are all getting summed. Okay, the observation is that when you increase any of the numbers like plus 3 plus 5 minus 7, the sum goes up, and when you decrease any of the numbers, the sum goes down. So any of the all right, the sum goes up. If we decrease, the sum goes down. Okay, nice. So for our problem, we are given an array. Fine, I'm not going to use any numbers. I'm going to use ABC. I can use numbers too, like they can be anything. Let's use the example. Okay, so in this example, we have given some items, and we are thinking of finding a triplet. So we all know finding a triplet is just finding a triplet and compare it to the target. We can do the problem in big of n cube way. Everyone knows that, but we need to be efficient. Finding a triplet from an array is a big of n cube, and the algorithm is roughly like this. Let's say this is our array. So for I in range, I'm doing Python. So for j in range I plus 1 index after I, so it should be, then this is our candidate sum. Candidate sum is so then we can do this stuff like comparing this candidate sum to target and then storing our results. We can all do that, no issues with that. Okay, with this code we are guaranteed to find every possible triplets, but the question is it really necessary to calculate all those triplets? Can we actually do something better? It turns out yes, we can. What we can do is, if we can, let's say, sort the array, we can sort the array, okay, and then we can utilize, because the sorted array, in the sorted array there will always like the lowest element is in the, if you sort it in ascending order, the lowest element is at the 0th index, then the second lowest element in the next index, blah 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 blah, and the highest element is at the last element of the array. So sorting works like this. Fine, no issues with that. We can sort the original array. That will take big of n log n time. All right, and the array is sorted. No, just all the elements of the array, we just sort it. All the elements are there, just in sorted order. We have not lost any of the elements, so all the elements are there. And we can use a trick here. The trick here is that we can, for our candidate sum, we have 3 elements for a sum, right? Triplets. Let's just denote them A plus B plus C. and we want to find out every possible triplets. And if we can reduce our search space, that's better. So one thing is every possible triplets considered, that can be done in cube, no issues with that. But how to use, so we're going to be focused on that, number 2. All right, so we just we went through, when we went with the naive approach, we went through every possible arrays in there, every possible items in there, like say -1 2 1, that's a triplet, -1 2 -4, that's another triplet. So we did that, right? We did it like this. So our candidates are like this, -1, I'm gonna increase, okay. So these are our candidates. So -1 2 1, this is a candidate. -1 2 -4, another candidate. -1 1 -4, another candidate. All right, 2 1 -4, another candidate. So these are all possible candidates. Okay, we went through our algorithm like this, but we can do better. After sorting our array, we'll go through each item one by one, but the other two items will be selected intelligently. How? Let's say we sort this array, we get -4 -1 1 2. So this is our new array, and for a triplet to form we need how many numbers? 3 numbers, and we will go for each of the numbers individually. We'll look at -4 and we are gonna figure out the potential triplets. All right, then the first potential triplet, we have, for that to happen, we'll have 2 pointers, one at the lowest side just after this and one at the highest side. So we are going to calculate the sum, -4 -1 2, and then we are going to record how closer is it to the target. All right, and the target was 1, so -4 -1, that's -5 2, that's like -3. So we get a candidate sum of -3, but our target is 1. So if we represent this in a number line, we see that -3 is here, 1 is there, 0 must be here, or something like that. And we look at what is at our hand. We are considering every possible sums that involves -4. Okay, and we can see that the sum is at a distance of 4 from the target. Okay, we are going to record the distance. The base distance right now is 4. The current sum, base sum right now is -3. Another observation is that as our array is sorted, if we were to, like, we are focusing on -4, right? But there can be any possible combination of these 2 items. We are not going that direction yet. So any possible combination of these 2 items can result in the triplet, no issue. But is that really necessary to go all possible n square combination? Because if you fixate it on -4, there are n square combinations, n-1 square combinations of these items. What we can do is we can think, like, our sum is -3, we want to be as close as possible to 1. How we can be as close as possible to 1? By increasing the total sum. How we can increase the total sum? By going up the number line. If we were to go this high value, go below this value, we would never reach towards 1. we would never get the best possible solution we are looking for. We'd only get inferior results. So what we do is we just get rid of this, uh, not get rid of this, we just increase the L index towards 1. So now our L index is here. So now we calculate the sum again. So we do not move, we have not moved the H, we just move the L. Why? We want the best possible answer, and the best possible answer will only be found if we increase the sum from -3. There might be best possible answers there. So the new sum is -4 plus 1, that's -3 to -1. So we just got -1, and then we are getting like two difference, and minus 1 is the sum and the difference is 2. So we just got a better answer. Then we will consider -1, and we're gonna look at the next two items. So when we are considering -1, when we are looking at -1, we're not gonna look back what was at the left of -1. Why? Because we have already considered this item. We have already considered this item when the indices below this index was considered. So that should be kept in mind. So I'm gonna add the code in the comment. So that's pretty much about it. We are gonna go through each item one by one, and we are gonna have 2 pointers, left, low and high, and we're gonna calculate it. So as we're gonna go through each item one by one and 2 pointers are involved, this is easily big of n square solution. One thing to note here is that we are doing kind of exhaustive search, but we are just not going in some search spaces where the best possible answers are simply not there. So that's how we are reducing from big of n cube to big of n square. What we're doing is we got our array. So we got our array, and all right, so we are going each item one by one. So let's get this one item, and we are considering this one and this one at the beginning, and now we are summing it up. So A, B, C, and A, we are doing this, and then we are comparing it to target. Our target is somewhere. All right, so this is our candidate sum. So we are thinking like, yeah, if our candidate sum is below the target for this combination A, B, C, if it is below our target, just observe this carefully. In this region, with this say A, B, C, these choices, so how we can get a better result? How we can do that? So if for this AB pair, if we move the C towards this section, there won't be any better results at all. Never ever, because that would only decrease the sum. So we are gonna get rid of this second, and we just move the P pointer, the low pointer to here. So this is our next P, so that we can reach closer to target. All right, so that is how it eliminates those big of n cube stuff. We are still kind of generating the triplets, but as we look at our current candidate sum, we are thinking of our current based result. So we don't need to search unnecessary spaces anymore. We have already got one sum, and that gives us, as the array is sorted, that gives us some sort of direction that will reduce those unnecessary searching.